Okay, excuse the brief interruption. That was actually kind of important. One of our counselors needed to talk to me about a student. Okay, so, and it was good stuff, so nothing bad. So what we've done, again, is we've added -1 times the second row to the third here. And we've done the same thing to the identity matrix. Now I actually wrote that one out here. To get the matrix E3, that's what we've done. Added -1 times the second row to the third, and we can see clearly that's what I've done. And then the inverse of that matrix, well, you would, if you wanted to get from here back to here, you would add the second row to the third, wouldn't you? Add the second row here to the third, and you're going to get this. So that adding the second row to the third on the identity matrix would give us this, the inverse matrix. Okay, then we need to get rid of that 3/2 there. So we multiply the second row by -3/2 and add it to the first. -3/2 the second plus the first. And that's going to give us the 0 here, -3/2 times 1, and -3/2 times 2 is -3. And add that to 1/2, we get -5/2. I didn't see that negative sign there. I hesitated for a minute and said, where did I get 5/2? I must have had my hand in the way or something. It's clearly there. Okay, so we get the -5/2. Now if we add -3/2 the second row of the identity matrix to the first, you can verify that this is what we get. And then to go backwards, we would add 3/2 of the second row to the first, and we'd be back to here. And we do that with the identity matrix, and this is what we get. Then we got to get rid of that 2, and also the -5/2. Now we could do that in one step, but we're doing elementary matrices, and we only want the elementary matrix to represent one step of the row reduction. So we begin by adding 5/2 of the third row to the first. The only thing that will change is this, and the -5/2 will become 0, as you can easily verify. We do that to the identity matrix, add 5/2 of the second row, of the third row to the first, and this is what we get. And if we wanted to go from here back to here, we would add 5/2 of the third row to the first. We would subtract 5/2 of the third row from the first to get this. And that's what we do to the identity matrix in order to get E5 inverse. And then the last step is we have to get rid of that 2, so we add -2 times the third row to the first, to the second. We get what we get. We do that with the identity matrix. -2 times this third row is going to give us a -2 here. Added here is going to give us the -2 that we see here. And the inverse transformation is to add 2 times the third row to the second, which we do here. So now we have the sequence of elementary matrices and the sequence of inverse elementary matrices. In the end, we started, and we can see that, and you can check this out. I'm not going to go through the details of it, pointing and everything. It'd be awfully hard to follow. But if I multiply this matrix by this one, I get this one. So multiplying this matrix by this matrix gives me the same thing as adding 1/2 of the first row of this matrix, or taking 1/2 of the first row of this matrix. And then this one times this one gives us this one. So each elementary matrix multiplied on the left by the matrix that we're acting on accomplishes the same thing as the corresponding row operation. So that starting with this matrix, we multiply it by E1 to get this matrix, multiply this by E2 to get this matrix, multiply this by E3 to get this matrix. Now how does that work? We start with our matrix here. Now I'm going to call that matrix A. So I'm going to let this be A. So that I begin by multiplying E1 by A to get this. So this is a matrix E1A. And then I multiply E2 by this to get this. Multiplying on the left. It won't work if you multiply on the right. Remember, matrix multiplication is not commutative, and you can check. Now actually, well, we won't go into that. In some cases, you might have a commutativity, but you can't count on it. So we're always multiplying on the left, and we always think of what we would do as multiplying on the left here. Then E3 times this one would be what? E3 times E2 times E1 times A. That's going to be this matrix. All right? So if we continue that process all the way down to E6, we're going to have this. Okay, and of course what we end up with down here is the identity, because we're reducing this matrix to the identity so that this equals the identity. What's that tell us? It tells us that the product E6 through E1 is the inverse of A. Now, I wrote a couple of things down here that don't seem to be necessary. So I'm going to take a chance and get rid of them just so I can emphasize what we've got here. Okay. So when I get down to the end here, this is going to be E6, E5, all the way down to E1 times A, and that's the identity. So this equals the identity. So E6, E5, okay, this equals the identity. So the product E6 down through E1 is going to be the inverse of A. Now you might think of what you would do if you augmented this matrix by the identity. And remember, if you augment this matrix by the identity and reduce everything down, you end up with the inverse on the right-hand side and the identity on the left-hand side. But if you do these operations to the identity, then you're just doing E6, E5 through E1 multiplied by the identity. That's just going to give you the same thing as E6, E5, E4, E3, E2, E1 multiplied together. So that product must equal the identity. Well, that's why the augmented matrix method of finding the inverse works. Now, if we wanted to get A, we could use the inverse matrices. Okay, if we know what the elementary matrices are, we can multiply them together to get back to the matrix A. Of course, there's no need to do that if we already know the matrix A, but to understand the structure of the matrix, we want to be aware of this possibility. So we'll talk about that in the next video.